What's the point of having a database if the data inside it is just wrong? If it's inconsistent, or if it completely falls apart the second more than one person tries to use it at the same time? It's basically useless, right? So today, we're going to dive into the essential guardrails that keep our data trustworthy and reliable.
So here's our game plan. First, we're going to start with the foundational rules that make sure our data is solid from the get-go. Then we'll get into the critical all-or-nothing principle of transactions. After that, we'll wade into the controlled chaos of concurrency, when lots of users are doing things at once. And finally, we'll check out some really powerful tools and fail-safes that help us manage all this complexity.
All right, first up, let's build a foundation of trust. This is all about making absolutely sure that from the very beginning, the data we're putting into our database is actually valid. And this really is the fundamental question, isn't it? Because if you let bad data in, everything else you build, all your reports, your analytics, your applications, it's all built on a shaky foundation. The database itself needs a built-in way to reject garbage before it ever gets saved.
The answer to that is constraints. The best way to think about them is as the bouncers at the door of your data table. A primary key is like the ID check. It makes sure every single row is unique. A foreign key ensures that if you're linking to another table, that thing you're linking to actually exists. And a check constraint is for enforcing your business rules, like saying, hey, the salary column has to be greater than 0. Simple, but incredibly important. So when we talk about creating those unique IDs, there are two common ways to do it. On the left, you have identity columns. They're simple, they get the job done, but they're pretty rigid because they're baked into a single table. On the right, though, you have sequences, which are way more flexible. Since they're their own independent objects, you can use one sequence across many tables, which gives you so much more control without having to change your table structure.
Okay, so constraints make sure valid data gets in. But what about when we have to do something complex that involves multiple steps? How can we guarantee that the entire process either succeeds completely or fails safely without leaving our data in some weird half-finished state?
A bank transfer is the absolute perfect analogy for this. Imagine the system takes 100 quid out of your account, but then it crashes before it can put it in your friend's account. Your money is just gone. A transaction prevents this nightmare by wrapping both of those steps into a single atomic unit. It means either both steps happen successfully or the system hits undo and rolls back the first step as if nothing ever happened. All or nothing.
This all-or-nothing idea is the A in ACID, which are like the 4 pillars of a reliable transaction. So atomicity is our bank transfer. Consistency means the database is always in a valid state and follows the rules. Isolation is what keeps simultaneous transactions from tripping over each other. And durability, well, that just guarantees that once a change is committed, it's permanent. It'll survive a power outage, a server crash, pretty much anything. And that I for isolation brings us right to our next big challenge. In the real world, you've got dozens, maybe even thousands of people and systems all trying to use the database at the very same time. So how do you manage that potential for chaos? And believe me, this isn't just a theoretical problem. If 2 people try to book the very last seat on a flight at the exact same moment, who gets it? If one person is running a huge report while someone else is updating the data for that report, what does the report even show? We clearly need some rules. And those rules are called isolation levels. This is where you hit a classic trade-off. The more you lock down your data for safety, the slower things can get. At the bottom level, read uncommitted, you risk a dirty read, seeing data that another transaction hasn't even saved yet. Move up to read committed and you're safe from that. But you might get a non-repeatable read, where you read the same row twice and get different values. Weird, right? Repeatable read solves that, but now you risk phantom reads, where new rows just magically appear in your results. Finally, at the top, you have serializable. It's the strictest of all, preventing all these issues by making transactions act like they're running one at a time. It's the safest, but yeah, it's often the slowest. A perfect real-world example of this trade-off is the with no lock hint in SQL Server. When a developer uses this, they're basically saying, hey database, I need this data fast, and I'm willing to accept the risk that it might not be perfectly up to the second accurate. It's a deliberate choice to sacrifice some consistency to gain speed. But all of this locking can lead to the ultimate database traffic jam, a deadlock. Think of 2 people meeting in a really narrow hallway. You try to step left, they step to their right, blocking you. You step right, they step left. Now you're both just stuck, waiting for the other person to move. That's a deadlock. 2 transactions are each waiting for a resource that the other one has locked. Total gridlock. So how do we fix this? Well, the database has its own solution. It detects the deadlock, picks one transaction as the victim, and just kills it. Problem solved, I guess. But our real goal as developers should be to prevent deadlocks in the first place. We can do that by keeping our transactions short and fast, and most importantly, by making sure all our transactions access resources in the exact same order to avoid that circular waiting game.
All right, for our last section, let's look at a couple of powerful tools that build on all these ideas of integrity and concurrency to solve some really common problems. First on the list is the merge statement. So imagine you get a batch of data. Some of it needs to update records that are already there, and some of it is brand new. Instead of writing a separate update and then a separate insert, merge does it all in one single atomic operation. It's incredibly efficient for syncing up data, a process people often call an upsert. But there's a catch. And this is a great reminder that there's no magic bullet in tech. In some database systems, like SQL Server, the very complexity that makes merge so powerful can, ironically, lead to its own tricky locking problems and even deadlocks. It's an amazing tool, but you have to use it with care, especially on a busy system.
Okay, next up, what if you need to run a massive, complex report, but you absolutely cannot risk slowing down your live production database with a bunch of locks? This is the exact problem a database snapshot solves. It creates a read-only, perfectly consistent picture of the entire database, frozen at a specific moment in time.
And this is just so useful. You can run those huge, long-running reports against the snapshot without affecting live users at all. You can use it as a quick way to go back and see what the data looked like before someone made a mistake. And of course, you can give your developers and testers a stable, safe copy of the data to work with. And that brings us to our final thought here. Through this whole explainer, we've seen this constant tension, this push and pull between perfect data consistency and real-world performance. From isolation levels to no-lock hints, the core engineering challenge is so often just deciding where on that spectrum you need to be. So the question I'll leave you with is this. In your world, when is good enough data actually better than perfect data?